Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to look at the Runge-Kutta method for solving first-order ordinary differential equations. We're going to be doing this using the fourth-order Runge-Kutta. Now, the Runge-Kutta, there are lots of variations on this, but essentially the development is a little bit like what you did for the Euler method, but we're using one of the higher order approximations. So we're doing half steps forward and back, I guess actually just forward, from our position in order to estimate what's going on at a particular point. So we get much more complexity, but we also get much higher precision. So our order of our error is going to be much, much smaller than it was before. Now, what we're going to do directly only applies to first order initial value problems, but we're going to see in a future lecture how to adapt that to higher order. Now, this is the formulation that I find is most useful. If we use h instead of delta x to represent step size, then we can represent the next y using the y from the last calculation plus 1/6 k1 plus 2k2 plus 2k3 plus k4 times my step size. And the k1, k2, k3, and k4 are evaluated based on the definition of the function at x and y and little steps away from there. And the little steps away from the y depend on previous values of k. But if you just treat these as functions and you know the definition of the function, this is not really all that much more challenging than the other. Now, the derivation is more challenging. I'm not going to put us through that at this level of a course. This is the algorithm for doing it. It's really very easy. You're just going to put in what your initial condition is. You're going to put in your step size, the range of values, and then you start the loop and you start stepping through and you do the calculation of yi plus 1 by calculating each of those k's and then using those with your step size to get yi plus 1. And then you keep doing that until you've gone through as many steps as you want and you print them to a table. So we're going to look at this, and we've done this problem before with the Euler method, and so we are going to now take this and adapt it for the Runge-Kutta method. So we have here my spreadsheet where I have in the initial value, I have my step size, and I have where I wanted to stop. So I'm going to stop when I get to x equals 10 in this particular case. And if I push this button, I've set it up so now then this will give me my answers over here in this column. So I can compare to this. I could also compare to the actual answers. What I want to do now is I want to do this using the Runge-Kutta technique. So if we come to Developer and our Visual Basic, it will bring this pop-up. And what I want to do is I want to start a new, and this is a fourth order Runge-Kutta. So, okay, I'll do that. And now then, most of this I can adapt by pulling in almost all of this here. I'll have to read in a little bit of additional information, moving locations and so forth. But really, I'm just going to copy this first portion of the program, and then I need to edit once I initialize and start my loop. So I actually have this over here, and I'm going to copy and paste this, and I'll talk us through what I've done. So start by reading in my sheet my data. So I'm going to get my a and the y at a. So this is my initial condition. And then I'm going to read in my step size, and then I'm going to read in my stopping point, so the b. And the number of steps I can calculate by b minus a over the step size. And then I want to initialize the loop for my calculations. So I'm going to start with x equal to a, And I'm going to go ahead and write that into my cell. Then I'm going to start the loop. So I calculate K1, and it's the function at x and y. K2 is the function at x plus 1/2 of the step size, and y plus 1/2 times K1 times the step size. And similarly for the K3 definition and the K4 definition. Y, therefore, is just simply 1/6 of, so I divided by 6, K1 plus 2K2 plus 2K3 plus K4 times the step size divided by 6. And then I increment my step size. And I write those values to the table, and I'm finished. If I do this properly, when I run this, this will always do Runge-Kutta for me, and all I'll need to do is change my function. And so remember, the function is set up so that the derivative equals something. And so this is my function here. So I can run this. And we see that it has populated the table. And you look at even way down here, 100 steps in, we're not very far off. The percent difference there is, small, 1% or so. So not too bad for having done 100 steps of a calculation. So this concludes this video lesson. In our next lesson, we will look at how we can extend this to higher order initial value problems. Thank you very much for your time.